Hello, everyone. So I will start. My name is Simon Corbin, and I work as a software engineer at CNES in Toulouse, France. And today I will share with you a quick overview of our activities regarding Linux for space applications. So just to begin, a few words about CNES. So CNES is a French space agency. We are more than 2,000, but regarding the onboard software team, we are only 10. And more specifically, regarding Linux activities, we are 2, so not that much. So just to give you a bit of context regarding spacecraft architectures, usually we make the distinction between the platform and the payload. So the platform will enable the mission by basically giving critical functions such as communications features for onboard communications with the ground, also attitude and orbit functions, or thermal regulation, for instance. So this part, in this part, we will find functions with a high level of criticality compared to the payload, where most of the time we will find more specific algorithm, which needs a specific operability, and most of the time they also rely on specific instruments. On this part, we will find I would say algorithm with a lower criticality, and we will focus on this part when we talk about the use of Linux for space applications. So this slide is just to say that basically the flight software is running on a processor, which is on what we call an OBC. OBC stands for onboard computer. Most of the time we have an OBC that is dedicated to the platform. We can also have an OBC that is dedicated to the payload, or also sometimes, it depends on the mission, but we can have only one OBC that is both dedicated to platform and payload features. So when we talk about onboard software architectures, I won't really talk about the first one because there is no operating system, so it won't really be interesting for Linux, of course. We have these two kinds of architectures. The first one is in fact not really used. We will find this architecture more on small instruments, or I would say for payload applications. And at CNES, most of our softwares are based on the third architectures. So basically we rely on a hypervisor, but I will give more details in the next slides. So, of course, these two architectures will be interesting for us regarding Linux activities. So, before talking more about Linux activities, I would just give a bit of context regarding the concept we use for our software. So we are based on TSP architectures. TSP means time and space partitioning. This concept comes from aeronautics, and it allows us to have strict separation regarding memory and time for our applications. So this is an example of what a flight software looks like. So as I was saying, we use an hypervisor. So the one we use is called Extratum. It's developed by a Spanish company, Fentis. And on top of this hypervisor, we have different kind of partitions. So the first, and the second, and the third one are, I would say, partitions that are generic, and we try as much as possible to reuse them each time we start a new mission. So if we think about the first slide, these partitions are more dedicated to platform functions, and then we will add mission-specific partitions. So at CNES, the three first partitions are what we call the basic software, and we propose them through what we call Cosmos. It's a new name, sorry, for LVC UGen, for the one who knows this software framework. So regarding Linux, it will be more, as I was saying before, for payload application, in our cases at CNES. And this is what I'm going to talk now. So why are we interested in Linux? So regarding the challenges we have now, it was very common to have like 10 to 15 years for development cycles, some not many years ago, but now it's very common to have more about 3 to 5 years for development cycles. So we have to adapt, and for that we maximize the reuse of software blocks. Also we rely on generic modular architectures such as Cosmos and Yocto, and also we have to adapt the process. In parallel, onboard autonomy is increasing, so there are many algorithms now that use AI on board. Also, we use auto-coding tools to generate algorithms, and of course, algorithms are getting more and more complex. So, the status today is that most of the applications are coded in C, and they are running on specific hardware for questions of radiations, for instance. We have many standards, so in Europe we use what we call ECSS standard, majority of grade B in our cases. And yes, space is a small community with not many supports, and in parallel, we have the complexity that is increasing. So thanks to new space, so I don't really have time to give a lot of details of regarding what is new space, but basically it allows us to embed COTS components. So who says COTS components says support for Linux in many cases. So what we could achieve with Linux, the one point that is interesting for us is the use of high-level languages. For now, there are many scientists that use, for instance, Python libraries for, I don't know, computer visions or for AI applications. If they come to us and we say you need to port your application in C, not sure they will be very happy. So that's why we are interested in the use of Linux, but it's not the only argument. Of course, there are plenty of compatible targets, and I don't speak, of course, of the community and a lot of support documentation we can find. But of course, it's not a magic solution. That's why last year we asked. We worked with a major space actor from France because, as you know, there are many standards, so many constraints. But the question was, okay, can we just write down what do we really fear? Can you just give us a list, a non-exhaustive list of what we fear when we talk about using Linux in space? And more than that, we also asked to propose and to give solutions for each element of the list. So the main idea was to give a basic list of requirements regarding a basic configuration for Yocto-based distribution, and many aspects were covered, such as real-time constraints, security, and so on. So if I show you some of the activity we are doing, there are, of course, different steps. The first one, which is not the most interesting, in fact, was to have Linux running on representative targets and also running representative applications on Linux. So this was the easiest part, but in fact there is a low interest because such a solution would lead to having a dedicated onboard computer running Linux on board. And as I said before, we are more interested in having Linux running with critical applications on board on the same processor. So this is the step we are working on now. It means having Linux as a guest OS in a partition on top of an hypervisor. And this case is really concrete now because it will fly on a student project for an AI application coded in Python. And the next step would be to have a kind of Linux-based app store. The idea would be to be able to have, I would say, the same usage you can have with your smartphone. I mean, okay, let's install an app for, I don't know, maybe 3 months, and once my experience is done, let's delete this app, and let's download, someone else upload his application on board for the next month. So this is let's say a future work, but for now we are not yet at this step. Just to finish, so to give you a bit of details about the distro we are using. So it's a Yocto-based distribution. We rely on a layer developed by Fentis for their hypervisor, allowing us to communicate with other partitions and, of course, use Linux as a guest OS in the partition. And at CNES, we are currently developing a PUS layer. So PUS is basically a communication protocol widely used in Europe for in space missions. And also we try to define what could be a minimal user app layer, giving some recommendations to the community. So what I would say is that we would be very happy to share the result of our current works, particularly in the frame of ELISA project and space-grade Linux. And I think that's all for me. Thank you. If you have questions, yes. With Linux or what?
Well, with like your hypervisor and
yes.
And you have it's in space now, or
without Linux, yes. Without Linux, yes. And we already have a partition with Linux as a guest OS, but it will be the partition that will be used in the student project I was talking. But for now, it's not flying. I would say in 2 years. Yeah. Yes.
Yeah. You already do OTA, and how would that differ from kind of what you're talking about, like the app store?
OTA, yes, but not for Linux-based applications.
Oh, I see.
Yeah. Yes.
Not really related to the technology, but just curiosity. There's only 2 of you right now in the space agency. How do you navigate the bureaucratic hurdles? Because I cannot imagine it must be easy to introduce Linux when you're just 2 out of 2,400.
Yes, it's not an easy job, but the activity is growing up. I would say the complexity is regarding the standards, because we can't imagine today saying, okay, let's qualify Linux for space, because it would take so long time to do it. So we are more looking at the activity we did last year. What do we fear, and how can we make Linux fly without really thinking about standards. So, yeah.
So actually, you have a control command like push. Okay.
It's under development. Yeah. Yeah.
So you want to also be compatible with another platform, because between the payload and platform, you have, I think,
Yes.
you do control command to send the element ground.
Mm-hmm.
So you can be compatible with another type of platform, because you have this, I think, in physical layer,
Yes.
maybe serial or
Yes, depending of the mission, but yes.
it's upgraded.
Yeah.
Okay.
Yes. Yeah. Any more questions?
Okay. So have you joined any of the SDL calls yet, or?
Yes.
Okay, I haven't noticed it. I think I'm on.
Yes, but honestly, I just subscribed to the mailing list. I didn't attend any meeting now, but we would be very happy to share with you and to contribute. Yes. Yeah. Okay, thank you very much. If there are no more questions.